Okay, so we are going to go over the notes that you may have missed on solving graphically. So this is in the purple foldable. And the first thing we want to make sure is that you put your name on it on the front. So please make sure you do that. And we're going to open it up to the first flap. So the first flap says solving graphically. And we are going to go through this whole flap. Okay. So we are going to name roots, zeros, x-intercepts, solutions. So for our purposes, really, we're going to treat these as the same thing. And we've talked about x-intercepts before, and we've definitely referred to zeros before. That was on the graphing calculator. So we're just looking for the x-intercepts here. So we have one here, we have one here, and one here. So x-intercepts are anywhere that it crosses or touches the x-axis. So that's our x-axis. So we have one at -1, we have one at 0, and we have one at 2. Those are our x-intercepts. So I can list those down here. Remember when we've seen this notation before when we did quadratics. And we're just going to list them typically in numerical order. Those are my roots. Okay, so that's a fairly unremarkable graph. We're going to move on to example number 2, which has something special about it that we're going to talk about a little bit more. So we're still naming the root zeros, x-intercept solutions. So this time we have one right here, and right here. So just a reminder, it doesn't have to cross the x-axis to be an x-intercept. It just has to touch. It can also cross. So this is x equals 1, this is x equals 2, and this is x equals 4. So there is something special about this graph in particular that we're going to talk about. And that is something called a double root. So right here, this is our double root. So it's a root, so it's still considered, an x-intercept, but it's special because you notice it doesn't actually cross the x-axis, it just bounces off of it. So it comes down, hits the x-axis, this is the x-axis, hits it, and then goes back in the same direction. Then, in this case, it crosses. And then in this case, it crosses. So this is special, it's a double root. So this is not a root. Some people think anywhere that it kind of like changes direction like that is a root. This is not bouncing off the x-axis. This is not a root at all. So when we list this, we could list it as 1, 1, 2, and 4. This just makes it really clear that I've got a double root right here at 1. Sometimes you'll just see it listed like this. So if you have to list it, you can just do it like this. When we list it like this for your purposes, we're going to give it to you like this just so that you know it's a double root. And then that's going to change kind of certain things about the graph. Okay, so let's put those things about double roots a little bit more specifically. We'll put them in this graphic organizer over here. All right, so double roots, when we're looking at them in an equation, it looks like a factor that has been squared. So if you think back to the quadratic parent kind of sits there at the origin. That is actually a double root. And if you think about what the equation of the quadratic parent looks like, it's x squared. That's why that's a double root. So it bounces off the x-axis. So it has to be the x-axis, and it has to be, we refer to it as a bounce. So it hits it, and then it kind of goes back in that same direction. So example, equation-wise, it could look something like this. So I've got a factor of x plus 1, and I have a factor of x minus 5, but this factor is squared. So I could use this factor to find my double root, or you can just refer to example 2 that we have over here. This is example 2. So you can just refer to that to see what that looks like. All right, a non-example would be something very similar, x plus 1 times x minus 5, except this time the 5 would not be squared. So this is not a double root. This would not bounce off the x-axis. Or you can see example 1. So example 1 had no double roots to it. They all just cross the x-axis, the 3 different intercepts. Okay, so that helps you kind of identify the double root, see what it looks like on a graph. And now we're going to talk about writing a root to a factor. All right, so we actually spent a lot of time, and you may or may not remember, factoring, solving a quadratic by factoring. We would get the factors, and then we would set them equal to 0, and we would solve for x. Now we're doing the reverse. So we're starting with roots. So roots look like x equals something, like right here. And then we're writing them as factors. And factors typically are in parentheses like that. Sometimes they're by itself if it's just like an x. So I'm going to show you how to do that. And it says right here, we're going to work backwards to make it equal to 0. So each of these roots are listed here, -3, 0, and 5. And we can write those as separate roots. Okay, so that's what that list means. X equals -3, it equals 0, and it equals 5. Now, those are solutions. So before, we were looking for those. This time, I'm giving them to you, and you're trying to figure out the factors that they came from. So we're going to work backwards. So instead of x equals -3, we want to make this equal to 0. So I've got to do the opposite, or the inverse, and I'm going to move 3 to the other side. So -3 plus 3, there's my 0. Here is one of my factors. Here's my x equals 0. Now, this is actually already done for us because I can add 0 to both sides, but that doesn't actually change anything. It's already equal to 0, so I don't have to manipulate it to look like that. It's already just x. So one of my factors is just x. And then my last one, I'm going to subtract 5 on both sides, and I have x minus 5 equals 0. So my actual factors are x. If you have a singleton like that, we're going to write it by itself. X plus 3 and x minus 5. So this is what we used to start with. And then you would set them each equal to 0, and you would solve for x, and you would get these other ones. Now we're doing the reverse. And the reason we're going to do this is because you're going to be able to look at a graph like this one. And based on these roots, you can write them as factors. And then actually what you're doing is creating the equation. That's where this is eventually going. So what you might notice is that really all I did was switch the sign. This was -3, and I wrote it as x plus 3. This was 5, and I wrote it as x minus 5. So really, if you want to make that generalization, and you don't have to show that algebra every single time, that's fine. But don't overgeneralize. So I'll show you why I'm cautioning about that. So thinking about what I just said, we can just rewrite this. So the root is -6. That means the factor is x plus 6. I'm just going to write it as the factor. So that's my factor. That's my root. Now, what you might be thinking is, oh, okay, so then I'm just going to write it as x plus 3/4. And I'm done. Except we are not going to do that. We have never, ever, 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 ever given you a problem that looks like that. If you think about all the times we've had a divisor, all of those divisors have looked like these factors. They've never had a fraction in them. Because that's not how we write a factor of a root that is a fraction. So let's talk about how we do that. We're still going to set it equal because it says x equals -3/4. And just like up here, I need to reverse what's there to get it to the other side. Well, I'm dividing by 4. So instead of dividing by 4, I'm going to multiply both sides by 4. So I've got 4x equals -3. And I've got to move that 3. So I'm going to add it to both sides. So I've got 4x plus 3. So now I've got my factor because it's equal to 0. So that's one of my factors. All right, and then let's try it with the half. So I've got x equals 1/2. I need to move that all to the other side, so I'm going to reverse it. Instead of dividing by 2, I'm going to multiply both sides by 2. I'm not there yet. I got one more step. I got to move that 1 over. So 2x minus 1 equals 0. And again, the reason I subtracted it is 1 minus 1 is your 0. I'm trying to get that to 0. So my last factor is 2x minus 1. So what some students have told me is that they do not love all of this algebra, and they saw a pattern, and they just extended the pattern to new problems. So here's the pattern they told me. They said, for fraction problems, they took the denominator, 4, wrote it in the front, switched the sign of the numerator, and wrote it at the end. So took the denominator of 2, put it in the front, switch the sign on the numerator, and put it on the end. If that makes more sense to you and you would prefer to do that, that's fine. Because eventually what ultimately we want you to be able to do is write this, because this is actually an equation, or we're going to turn it into an equation. So that's all the notes that you need.